Good afternoon. Well, let's get back to work. I haven't actually been doing too much recently, so I have no excuse. Alright, so what we were working on is we were working on taking all this information that we've gathered, turning it into our flow field. And we came up with our 7 steps on how to actually do that. Now I just gotta go do it. Oh, Lucas, I'm doing well. Just taking a few days there, hanging out with family, going and doing things, which I'll also be doing tomorrow, but that's how it is. Alright, so I need to get back to actually getting these textures written properly. What about yourself, Lucas? Any more sailboating adventures? No, it does not work unless you are a sub. I'm sorry to say. Anyway, it doesn't have a T in it. Alright, so where were we? I was working on step 1, which was go through all the pixels, detect the hard short edges, and write the direction surrounding the pixels that are non-short within radius, and the magnitude should be a small constant number. Yeah, see? Doesn't work. Alright, so here we go. It's this generate flow field function right here. And let me normalize everything. Alright, so write the shore edges. Then we need to write all the paths. Alright. Let's see what this right shore edge actually does. So we go through the entire map width and height. We grab our distance data, we go from edge radius to not edge radius, and we write the position plus equal the... So we have a non-normalized sort of thing. The former CC actually accidentally ending your sentences with semicolons. Yeah, and then you end your semicolons and semicolons, and it just gets worse from there. Alright, so this is going to generate... This will write the shore edges to the data field, and the result will be non-normalized weighted vectors. Let's check these files out. Yeah, I won't be streaming tomorrow. I'm going to be going fishing with my dad. We're going to go kill some more creatures. I don't even know what these are anymore. Alright. So you got writing of the shore edges. We've got our basis, all this stuff. Okay, so Result is not normalized. Okay, so the next step is iterate through all calculated paths, set direction. I guess maybe I should normalize and then I should probably normalize it afterwards here, and then multiply by the, yeah, I think that's probably the right result. Will be normalized directions with a, well, they're not normalized directions, it will be direction vectors with constant magnitude. Alright. Alright, we'll see. Result is still not normalized. Alright, so we want to go through all calculated paths. So write calculated paths. Let's see, we're gonna want a path magnitude. Let's just set it to 1. So it's going to be max magnitude. Should I write a radius for this, the calculated paths? I mean, probably not, because the particles will come in and actually get it all sorted out. So I think I'll just start off with writing the actual paths. But I'm just going to do a path radius here. Or should I? Let's just not. Just keep it simple to start with. Alright, so write calculated paths. That's going to be our next thing. This will write out our calculated paths to our flow field. Alright, this is a float magnitude, and this will be a T-array of calculated flow pixel for reference. Alright, so we got the calculated flow paths. We are going to go through all of our paths. So where are our paths? Alright, so it's going to be for calculated flow path. Path, and in paths, we are going to write out our calculated path. So is it path dot what? Path dot path. Well, I guess what I should do is I'm going to need the direction of the actual path. So the path is in reverse order. So we're going to want for int 32 I equals path.impath.num minus 1. I is greater than or equal to 0, and then minus minus I. And why don't we just skip the last one, so we're always good to go. And we'll get our direction by taking the next node and getting the direction to it. So let's get our next node and our current node. So the direction is going to be what, next node dot We just have X and Y. So the kernode.mx and then kernode.my, and we're going to need to subtract next node.mx minus. I really hate how autocomplete just deleted kernode. See, like, why in the hell would that delete that? I really don't like autocomplete on, like, literally anything. It's like, get out of my face, I know what I'm typing. IntelliSense does not know what I'm typing. If it did, it wouldn't suck so bad. Alright, so we're going to say our pixels, so int32 index is going to be kernode.mx plus mmap.mwidth multiplied by path kernode.my. And we'll just say pixels subindex dot cos equals what, dir? It's an f vector 2D. Alright. And we'll have our f vector 2D here. And we're going to say pixels subindex dot path equals true. Alright, so I should write all the paths and should write all the things into the paths. Then we're going to have a normalize step in here, aren't we? I'm not sure if we're actually going to normalize the field. I mean, we'll want to normalize the field, and I guess the pix.mag is what we're really going to need. But we'll figure that out. So let's make sure we wrote our calculated paths properly. Man, it's Saturday, right? Man, it's like the weekend and everything. It's like that doesn't matter when you're self-employed. I still got this gnarly, like, half-inch long mark from where this splinter went under my fingernail last week. It's going to be there forever. Alright, so how was I calculating all this stuff last time? I think I was clicking on this, construct a static flow field, and then just calling, like, generate flow field on it, something like that. So I construct static flow field, then like tick flow field, and that ticks it for like 75 times or something. And then we call generate on it, I'm pretty sure. Alright, so we've got our path written out. Looks about right. I don't see anything wrong with that. Alright. So now what we need to do is iterate through all the particles, look at their history, the average historical direction, this is the direction, magnitude should be distance traveled in history. Alright. We're not even using this path magnitude, are we? No, we are. Alright, good. Alright, so 3. Go through all particles and record their data. So we're going to do the particle magnitude and the pixels. This will be called to write particles to the flow pixel grid. Alright, so write those out, and what we're going to need is the actual particles. Where are they? They're inside of the map, I'm pretty sure. Yeah, there they are. Okay, so for every particle inside of this thing, we're going to want effector 2D direction and float mag. And we're going to overwrite the shore, I think. Or should we average in the shore? I think we'll average in the shore. Alright, so we'll have our calculated flow pixel. Pix is going to be pixels subindex. Alright, so let's see. Particle .m position history. So let's see, what should I actually do here? I mean, all these movements are going to be single movements. If we have this particle history, it's going to have a history of where it has been. I mean, we could basically take all the average positions and then the current position, add them together and divide, and then that's the direction. Might not be a bad idea. Why don't we try that? So get a 0 vector on that. Magnitude, well, we'll figure that out. Alright, so the position history, so it's going to be direction dot x plus equals what, particle dot msx. So I'll have the start x, the start y, and then we're going to go through everything inside of the flow path particle history. And we'll have like n32 num equals 1. So even if we don't have anything in the history, we're going to take our sx and sy, and we'll be able to get our direction from there. If our direction is nothing, then we're going to write nothing. So not a problem. So direction plus equals hist pos and num plus plus. Alright, so direction divide equals by num. It'll average our position, and then the actual direction is going to be the particle.mpos minus direction. Direction dot normalize direction times equals particle magnitude. Now the question is, should we go through the history positions themselves, like where we've been, and try to fill all those pixels with our direction? Because as these particles have been traveling, we could use that information as well. We could actually write the... We could actually just use it to write the history. Like, we already have the history of where this particle has been. And we can just say, well, you're supposed to be going towards, you know, this position where we are now. That would not be the worst thing ever. Why don't we just go ahead and write that? So we add together all the values to get an average for the current position, and then write in all the history blocks. So this will be an overwrite. The direction to current position. Alright, so what we're going to do is f vector to the hist direction is going to be particle dot m pos minus hist pos, and hist direction dot normalize hist direction times equal particle magnitude. And we'll say the index n32 hist index is going to be histpos dot x plus map dot width times histpos dot y. So hist pixel is going to be pixels at hist index. If hist pixel dot particle or hist pixel dot path, then continue. Let's just do equals false. and throw all this stuff inside of it. That way it's a little bit more portable. The continue might screw us up a little bit. Alright, so pix.particle equals true. Did we set path to true? Yeah, we did. Good. Alright, pix particle is true for the actual particles, and we're going to say pix.pos equals direction. Alright, so we've got that sorted, it looks like, so why don't we go ahead and see what it looks like. So we've got our paths, we've got our particles written. The next one's going to be a tiered average, then a rough blur pass, and then a fine blur pass. It looks like instead of using the particles history to create a magnitude, I'm actually having their particles, the trail of the particle, right in itself, which should be pretty good. We'll see how this looks. I have absolutely no idea how this is going to work. So construct it, ticket, and then we'll generate. And I have absolutely no idea what it's going to look like when we're finished. Though it's starting to look cool. I mean, even if we just had this shore avoidance and some of this stuff, that's almost just good enough in some insane way. That's actually pretty good information. Oh God, what have we done? Well, that just looks like corrupted data, to be honest. So let me see, why would it be corrupted? Oh, we're not even writing the historical pixel. I guess I need to do some Let's actually look at this position history. Let's see if it's getting written to properly. We're going to add in pause. Alright, so what's probably going on is this is fmath floor to int just not working properly. And we're getting some real odd behavior, which is just slashing this thing all across our map. Alright, that should do that. And we're not actually writing to our hist pixel. We also have the velocity. Interesting. Perhaps we shouldn't take the history into account. We should just take the velocity in the initial direction, perhaps. I don't know. It's a good question. I could do the max velocity. I'll write down a few questions. So, should I take the velocity of the pixel into account? When writing the pixel, should I scale the magnitude of the written vector by the max velocity? I mean, probably. I'll have to figure out how the velocity stuff is all supposed to work. I'm not exactly sure right now. I just want to see some general stuff come together properly, and then that'll probably be enough. So this will be it. Work on water flow field. Sunday is going to be fishing. And it's almost August. What a concept. Alright, let's run this thing. Alright, let's see how this goes. Let's construct that static map. Let's check out our files. Let's take our flow field. And what's also interesting is that our path got blown away. I would have expected our path to still be there, so something got all screwy. I think it was our index calculations. I don't know, let's see. Our index for every particle in our particles. Yeah, see, this looks a lot more reasonable. And that's interesting. We overwrote all of our stuff here, so obviously some particles are existing on top of our flow field map. Alright, so let's think about what this is doing. So all these paths are showing their direction. So all this water is going in that direction, all this is going in that direction. This is going more this way, that way, that way. These ones are kind of going this way, and these ones are going kind of more yellow, so they're going this way. These ones are going towards it. Red. These pixels are going this way? Got some odd directions. Green and yellow are kind of this direction. Well, that looks pretty decent, actually, to be honest. Like, we don't have a whole bunch of information here, but that's fine. We have a whole lot of information everywhere else. And we have way too much information over here. So these are going this way, and these are going kind of this way. So if we were a little dude, we'd go whoosh, whoosh, out into the night. That's fine. That's actually perfectly fine. Well, thank you, Hardcore Finesse. I'm just messing around. I'm trying to create this flow field thing for water so that like this will actually be a body of water. And we're combining all this information, like this is distance from shore, and this is like our particle simulation information. And we've got kind of our height map and our distance to below us map kind of written in here. Like you can see there's something down there, so we go look and it's like, there's a mushroom just sticking in the middle of nowhere for some reason. And we're trying to make our flow field out of that. And this color is actually written as a three-dimensional vector in world space, so we know which direction we're supposed to go. The color is a little bit difficult to read because 0 to 128 is like negative, and then 0 to 127 is negative, and then 128 to 255 is positive or something like that. So it's kind of hard to see exactly what everything means. Like, why is this blue over here and all that? It's mainly because the blue is always like the z-axis is up, which is blue. So a 0 is going to be 127, so it's always blue if it's 0 pretty much. So it can be kind of hard to do. Well, maybe. I'm learning stuff too. I've never written out flow field information stuff. I like how we've got this little preview here for this color texture, and then here's the actual texture. The texture's blank, but it's all hidden information. Alright, so what's not happening here? Our line here is wrong. We need to not write that out. We need to not overwrite information. Alright, so if pix.path equals false, then we'll write this actually, why don't we just do if pix.path then we'll just continue. So what else are we getting here? Well, we're getting everything that we need, so that's fine. I think now we don't have the magnitudes written in, and I'm concerned that the magnitude of all these things is going to just make this water go super fast. Like, we're going to have to Why don't we get the directions right first, and then we'll work on the magnitude of everything, and that'll just be like step 2. So let's go ahead and save all this and close it and implement the next step. Which is, the next step is there's a lot of pixels here where nothing's written. That's the white pixels. Well, they're gray, but for our directions, that's a 0 vector because it's 128, 128, 128, which is kind of a dirty gray. We don't have the pix until we actually calculate this out there. Let's just confirm that the path isn't getting overwritten, and then we'll move on to a tiered average for every level. So what we're going to do is, we're going to go through every pixel on this thing. We're going to then create a tiered average, a whole bunch of grid squares. It kind of looks like this, where we'll have a whole bunch of stuff get averaged together with, it'll start with smaller squares and then get to bigger squares and bigger squares, and there'll be weights based on the height of the pyramid, because kind of how this will work is it'll create a pyramid mathematical structure. Actually, it's kind of an inverted pyramid. And that should allow us to weight averages in our area pretty nicely. So we'll do like one path to fill out this data structure, and then we'll do another path to do the other things. So what are we talking about now? Well, once I've got the particles written here, I need to verify that this path doesn't get blown away, because we need that path to stay there. We're going to need to figure out a good way to fill in all these blank spaces. So the blank spaces are all zeros, and we're going to basically be taking an average across our texture and applying that, but it's going to be like a locale weighted based average, and the computation for that would be too much per pixel, so we're going to make like a giant pre-computed thing, and then we'll just look up our answer. Alright, good. So now we're not blowing away our path values, which is what we need. And if you're curious about how we're actually figuring our inputs and outputs, these green blob things are inputs and these red blob things are outputs, and they have these pieces of geometry. Like this is a square or a cube, rectangular prism based output, and this is just a sphere based input. It's like when we hit play, we don't see those inputs and outputs. They're kind of editor only little widgets. And some of these like objects like this waterfall actually has that stuff kind of built into it. So like if you added a waterfall, to the scene, it would just automatically have its inputs and outputs set up, so you don't have to screw around with stuff. It'll just, hopefully just work. Okay, so the next thing is this tiered average. So let's get to work. Hello, Synchron. I'm back to writing out the flow field information. Alright. This monitor is not set up properly. It's like this monitor is propped up by the collection of Game of Thrones books that I have. And of course, like, Game of Thrones is back out, so my mom has like stolen one of the books. So it's not very well supported at the moment. It's missing a few chapters. That's how all the professionals stack up their monitors on their desk. It's just a whole bunch of random crap that you have around your place. It's actually pretty hilarious at Amazon, where you get these desks, which are real crappy wooden desks, and you wouldn't have anything to like put your monitors on or like elevate them, and your monitors weren't super like amazing monitors like some of mine, I can just like move them up and down. Like I got some fancy ones. So what you would do is you'd basically build all your desk area out of just tons and tons of printer paper, because we had unlimited printer paper because we're, big corporation. So you'd go to the printer, the office area, and you'd grab like 10 big things of printer paper and just build out your desk basically. I remember one time this guy was walking out of the office with like maybe like 20 of these 20 packages of 8 by 11 paper. It weighs like 100 pounds or whatever. And it's just like, man, that looks expensive. And he just like turns his head. He's like, not for me. He just keeps going. It's like, shh. Corporations. All right, so we need the tiered average for every level applied across. All right, so right tiered average pixels to pixels. All right, so this will be tiered magnitude. It's like what that one book, Heart of Darkness, where it's like the one thing we've got is rivets. We got tons of rivets. If we can solve a problem with rivets, we're gonna solve it with rivets. That's how insane reality is. It's like, well, can we solve that with printer paper? Like, well, we could use, like $100 worth of printer paper to solve this. Be like, all right, well then we will, because that's free for us. We don't pay for that. So, call to write the tiered average, direction, and magnitude for our blank pixels. You have way too many streams. Well, that's a good thing, Lucas. You have so much content, you cannot hope to consume it all at once. Amazon makes you pay for the paper? No, they didn't. That was the problem. Is because they didn't make us pay for the paper, we just took it. Just did whatever you needed to. Like, I need a footrest. All right, cool. All right, Sanacron, I will still be on here. I've only been going for like less than an hour, so should be good. So do I need some sort of specialized data structure for this thing? Or can I just kind of wing this without a real complicated piece of fanciness? Alright, so what is this going to be? We're going to need to make half-sized things, so I mean, why don't we just make a data structure for this? Alright, so our levels, tiered average level, yeah. So int32 m level, then we're going to have our actual stuff. Let me just make these structs because I don't really give a damn. Alright, they're just going to be data anyway, I'm pretty sure. Alright, so we're going to have an f vector 2D for everything, and that's going to be mdir, and we'll have float mmag. So a level is going to have a t array, of tiles. And the holder is going to have a T-array of levels. Why don't we go ahead and make this a class? So our methods are going to be like void right pixel, and we'll throw a calculated flow pixel in here. And we're going to want to get information for a specific tile. So we'll have like void get info, we'll pass in a pix, and then we will get out. And f vector 2D, get a direction and a magnitude based on that. And we're going to have an init function, which is going to take an int32 width and an int32 height, and it'll fill everything out. So what this is going to do, I'll draw this out real quick, is sometimes it's easier to draw out what a data structure looks like than it is to explain it. So kind of what this thing is going to do is we've got like this map, right? And on this level, which would be the entire map, you would have one value, which would have like, you know, the average direction. And if, you know, we're starting here and we're ending over here, the average direction on the map is probably going to be something like this or something like that. Or it might even just be straight down because there's so much stuff over here. But as we subdivide this thing, kind of like this, kind of like that, what we're going to have is we're going to have averages on every level of this thing. So like an average on the entire thing level, we're going to have an average on like this half of the map or this quarter of the map. We're going to have an average for, you know, this section here, and so on. So if we weight those together, you know, a high level one like this and a low level one like that, and then, you know, like we average these all together, we'll get kind of our local direction for these pixels that don't have any representation. So that's kind of what we're trying to write right now. Alright, so what we're going to have is our holder, and we're going to have holder.init, we're going to do mmap.mwidth, mmap.mheight, and how many levels are we going to have here? I guess mmap.mwidth divided by 2. And then what we're going to do, I need to fill in these functions, and I will, but we're going to do holder.write particle. That's actually going to be for every pixel, pix in pixels. I'm going to write this in there. And then what we're going to do is we're going to go through, well, that's every pixel want every pixel that actually has something written to it. We don't want to average out a whole bunch of zeros, so if pix.pos does not equal f vector to the 0 vector, then we'll write it. And that'll be fill in all our averages. So for every in pixels, we're going to say if the pos is actually this, then we're going to say f vector to the dir and float mag. We're going to call holder.getInfo. We're going to pass in the pix. We're going to pass in the dir and mag, and then we're going to say pix.pos equals dir and pix.mag equals mag. And we'll multiply by a tiered magnitude. Alright, so then all of our logic for how we actually calculate all this crap is going to be inside of our init functions and all the rest of this stuff. Alright, so the initialize is going to have to go through let's just be lazy. We'll do a while true loop, which you should never do, but whatever. Let's say int32 cur width equals guess maybe I should just do the max levels and everything. And we'll start it at 1. So we don't need the no, we do want everything. Alright, max level. So cur width is going to be width divided by 2 times the instead of I, we'll just do for level equals this. Level is less than max levels, so it's going to be 2 times level. So two times level. A lot more things here, aren't I? We're going to subdivide this thing pretty big. We're going to want like we don't want to make everything because then it goes down to like these tiny squares that are the size of a pixel. We want kind of, we don't want everything being modeled out here. Alright, so if level equals 0, then we're going to need to make every level is going to have tiles. Alright, so level equals 0, then, alright, so why don't we do it this way? Cur width equals width, and 32 cur height equals height.